Welcome to another RDWorks Learning Lab. I've dug up this picture of an old girlfriend of mine, but don't tell the wife. And I'm going to use this as a starting point for today's subject. Now, lots of people have asked me, how do you go about laser etching a photograph onto a piece of material? Now, it's a very simple question, but I'm afraid there's quite a lot of technicalities behind it, which have taken me quite a bit of time to fathom out. I'm not going to show you today how to prepare the picture. I'm not going to show you today how to print the picture. There are two big sections that you need to understand. One of them is what this picture is before you even start working on it. And the second thing is all to do with this parameter menu. And if we take a look just here where the cursor is, you'll see that we've got something called an interval in millimeters. Now, it's only a little window, but it's probably the most important thing that you have to work with and understand when you're preparing pictures to go out to the laser machine. We'll come back to this interval, but before we deal with that, we ought to just have a quick look at what this picture is, what sorts of pictures you can get, and how we work with them. But if we are using RDWorks, then we can only be using a Windows machine. And if you're using a Windows machine, you can go here to your All Programs and you can select Accessories. When we find it, there it is, Accessories, and you can select Microsoft Paint. Here we are in Microsoft Paint. I've imported a slightly different picture. Now, this particular picture may look a rather grainy sort of grayscale picture, but in fact it's not grayscale at all. If we look carefully at this picture, there are only two colours, black and white. Let's just zoom in and I'll show you what I mean. Now, the laser should find this fairly easy to deal with, because all the laser tube has to do is to switch on for black, where it'll burn a mark, or off for white. So as it scans across this picture, the laser beam has to turn on and off incredibly quickly to paint these dots, either black or white. Your eye and brain combination are a wonderful pairing, because they see and interpret this picture as a grayscale picture. The black and the white are mixed by your eye and interpreted by your brain as shades of grey. It's very clever. But let's now go back to the picture that we started with, and you can see that there's obviously a difference in clarity, because this is a continuous grayscale image. Now, what is a grayscale image? Well, a grayscale image is one where we've got white here, which is set at a value of 0, a digital value of 0, and we've got black, which is set at a digital value of 255. If you start mixing black and white, you get grey. So between those two extremes, there are various mixes of black and white, and in fact there are 254 mixes of black and white in that picture. Right, now that we've zoomed right in on the picture, you can see that that's not a continuous picture either. That's a picture made up of little teeny weeny squares. In fact, the resolution of this picture is 300 of those squares per inch. 300 dpi, dots per inch. Sometimes it's pixels per inch, ppi, but it doesn't make any difference. That's what you're getting. And if you look carefully there, you can see these shades of grey. Each pixel is assigned a colour, and each pixel is mapped onto the screen, and that's what a bitmap is. It's a definition of the picture. Every element of that picture is mapped into memory, so it can be quite a huge file. With all those shades of grey in the picture there, how does the laser deal with this picture? Because the laser beam can't produce different shades of grey. The only thing that the laser beam can do is burn a mark. First of all, let's assume that we're going to burn this picture onto a piece of white card. And let's just take a look at any one single scan line that's got to go across this picture. So it starts off on the left hand side with no power at all because we want white. It will track across until it gets to the first hair. It then comes across a very light shade of grey where it will put in a very small amount of power to just lightly scorch the paper. So as the laser moves across towards her eye, for example, where we've got lots of dark colours, what will happen is the power will increase dramatically and we will hit the black areas with the maximum amount of power that we can to put the burn deep. Now it'll get deep, and because it's a burn it'll probably grow a little bit as well. So we shall get the impression of a darker shade. It's still the same colour brown, it's just burnt a bit more. And that's how we will produce this picture. The power of the laser gets changed incredibly quickly as it scans across a single line. It's a continuously varying power. You may have noticed on your machine and in the software that there is a facility to specify a minimum power as well as a maximum power. Well, what we can do, we can actually soften this picture or make it harder by changing the levels of power that we put into our program. If, for example, we put 30% power minimum and 70% power maximum, what would happen is the white would start at 30% and the black would be at 70%. So between 30 and 70% power, we would have 256 increments to work with. But of course, the change of power between 30% and 70% is not very much. So instead of having a nice contrasty black and white picture, what you'll have is probably a bit of a muddy, dull picture. But that's the sort of thing that you can experiment with. That's why the max and min is here. It's to play with during scan mode. Well, what we've looked at is two different types of pictures and two different ways in which the laser beam reacts to produce the picture. Now, there are benefits and disadvantages to each of these picture types. Now, most people go for the dithered picture rather than this grayscale picture because somehow the results seem much more pleasing to the eye. Okay, now I've cleared the screen. Well, maybe not entirely, because if you look up at the top left hand corner you'll see a little black dot. Now that little black dot, if we look down here, it tells me that it's 74 pixels by 71 pixels. Now that's the size of the white square around the outside of the black dot. I believe the black dot is about 60 something pixels. Now I've purposely created this crude, very coarse resolution picture because it's going to demonstrate the principle that still operates on the high resolution pictures. Okay, now we've imported that same file into RDWorks. What I'm going to do, I'm going to draw a square. Now I'm going to draw a square for a very good reason. I want to measure what that step is. So if I draw a square from there to there and then put handles around it, I can come up here and I can see what size that square is. Now it says it's 0.27 square. Now I want those pixels to be around about 0.4. Now behind the scenes here I'm going to have to just use my calculator a minute. I want to finish up with a little square, a pixel of about 0.403. 0.403 divided by 0.27, it was 149.25%. 0.404, that's good enough. Okay, so now I've put a handle round there and we're going to go up to handle, bitmap handle, and here we get information about the object we've got on the screen. Now the first thing it tells me, if we look here, is we've got a pixels per inch 64. Okay, now that's the only information that I need off of here. So if I go to my scan parameters, output, yes, speed, let's choose 300. It's a scan. We haven't got two heads. 30%, that seems quite reasonable. I'm going to be scanning backwards and forwards, not single scan, because one of the other options that I've got here is something called X unilateralism, which basically means I'm going to scan, come back, and scan only in one direction. Now, there are certain advantages to doing that, but it's going to take twice as long. So we'll live with the X backwards and forwards scan to start with, but then we've got this interval value, 0.1. Now, what should it be for this picture? Well, I'm afraid it's now time that we've got to do some fairly simple mathematics, and you'll have to do this every time you deal with a picture. The first thing you must do is look at the resolution of the picture, and in this particular instance we checked with the bitmap handle and we found that the resolution was 64 dots per inch, or 64 pixels per inch. Now note, it's per inch, whereas the scan interval that we've got to fill in is in millimeters. So already they're in totally the wrong units. We can't just stick 64 or some strange number in that interval. We've got to rework it back to a millimeter interval. And the way that we do that is to use the conversion factor that 25.4 millimeters equals 1 inch. So now we've got two simple mathematical steps to carry out on your calculator. The first one is to divide the dots per inch by 25.4, and that will tell you how many dots per millimeter. And then, because the interval is per millimeter, per 1 millimeter, what we've got to do is we've got to divide 1 millimeter by the number of dots per millimeter, and the ideal number that we're looking for is 0.397. Now I'm going to go through a little bit of a tedious exercise now. I don't need to take you along with me, but I'll tell you what I'm going to do. I'm going to set that interval to 0.1, 0.2, 0.3, 0.4, and then I'm going to set it to 0.397, and then I'm going to go 0.5 all the way up to 1 millimeter. So I'm going to produce a series of patterns with different scan intervals on them, and then we'll come back and look at the results. Now, in looking at these results, two things I want you to remember. First of all, my dot size is around about 0.2 of a millimeter, i.e. that's the thickness of those lines, 0.2 of a millimeter. The second thing is that the picture that this was developed from was a pure black picture, which basically meant that as the scan started on the left hand side, it went to full power and continued all the way through to the other side and then stopped. So we'll quickly run through the results. This one was set at 1 millimeter interval. This one was 0.9. This one was 0.8, 0.7, 0.6, 0.5 and 0.4, and that is 0.397. Right, we'll just stop at this one because this is ideally the perfect step size. And let's take a look at what's going on. We've got a line thickness of 0.2 and we have got a step of 0.4. So therefore we should have a 0.2 gap between each one of those lines. But the only reason we've got that gap between these lines because I've chosen a very coarse resolution for this picture, 64 dpi. Now if I'd have chosen probably 120 dpi, those lines would now be touching. Okay, I hear you say, well, we'll just move the lines closer together. Yeah, it isn't quite as simple as that, because let's change the pitch now the spacing, the interval, to 0.3. All of a sudden the software has become totally confused. It doesn't know whether to draw a line or not draw a line. There's all sorts of gaps, overlaps, strange things going on. That's 0.3, which is only a small error from the 0.4. Bearing in mind we're talking about millimeters, so that's only 0.004 of an inch difference in the pitch. Okay, you say, well, maybe we ought to double the pitch. Then it would be a nice even number. In other words, instead of going 0.4 pitch, let's go 0.2 pitch. Then the lines will touch. Here's what 0.2 pitch looks like. Pretty messy as well. And when we get down to 0.1 pitch, there's an even bigger problem. Now, those are patterns that would overlay your photograph and cause all sorts of strange artifacts in your picture. So what I'm trying to tell you here is that the only pitch that you should be using is the calculated pitch. Okay, so we've seen what happens when we choose the wrong step interval. If it's big, it doesn't look very pretty. If it's small, you can get all sorts of artifacts. Now, we ought to just again stop at this point and point out one other major factor that you've got to take into account. If we take a look at the second line there's something called spot size. Now, spot size is the smallest spot that you can burn with your lens. Now, a 1.5 inch lens probably can do better than 0.2. A 2-inch lens will probably do around about 0.2 millimeter spot size, which is also the width of the line that it will carve. Let's just take a look at how many spots or lines we can get in 1 inch. Now, 1 inch is 25.4 millimeters. So if we divide our 25.4 millimeters, which is 1 inch, by our spot size, which is 0.2 of a millimeter, we find that we can only get 127 dots in an inch. Now that's quite a coarse looking picture, 127 dots per inch. But the point is, if you start going greater than 127 dots per inch, you will start overlapping your dots. Now, there's nothing wrong with overlapping dots, and probably you might even want to go up to something like 250 or 300 dots per inch as being the sensible maximum that you can get out of a picture. If you start going much more than that, all you'll start doing is overwriting the dots that you've put in, and it might start to look a little bit messy. Now, what I've done with this particular circle now is I've reset it to a different resolution. Now, I've chosen a pixel size on this drawing now to suit my line width, in other words my spot size of 0.2. And if we take a look up here at the bitmap handle, we'll find that what I've got is a resolution of 129 pixels per inch, or 129 dpi. Now that's not perfectly 127, but it's going to be near enough. So what we should do is calculate the resolution again at 129 dots per inch, and 129 dots per inch divided by 25.4 gives me 5.07 dots per millimeter. And then if I divide a millimeter by 5.079, I find myself with an interval of 0.197 millimeters. And 0.197 millimeters is not far off the pixel size or the spot size of 0.2. When I produce this circle, I'm hopefully going to get laser lines that touch each other. So let me go and do that, and then I'll bring the results back and we can have a look at them. Well, here's the result, and as you can see, we have got a nice set of straight lines that butt up to each other and produce a nice shape. Now we're nearly at the end of this session, and if you haven't spotted it for yourself, I'm going to tell you that the most important factor that you need to consider when you're trying to laser cut a photograph is this feature here, the spot size, the ability of your lens to produce a certain diameter spot or line width. Now, there is no point in you choosing, for example, a 500 dot per inch photograph, thinking this is a great resolution, we should get fantastic output. It might not be quite as amazing as you think, but it's something you should experiment with, because what's going to happen is if you choose a 500 dot per inch resolution photograph, then it's roughly 4 times greater resolution than your spot size. So by the time you put this in here at 500 dots per inch, you're only going to be moving down about 0.05 every interval. And so what that means is you will only be moving down a quarter of the spot size for every scan line. Now, apart from the fact that it's going to take you absolutely ages to produce a picture, it might not be a very good quality picture by the time you've finished. So you need to think about your spot size, and you'll need to experiment to find out what the best resolution pictures and the best interval is for you to use. And then the other thing to consider is the material that you're using, because depending on the material that you're using, the quality of the picture can vary greatly. For instance, if you're using a soft wood, then probably what we've got here, 129 dots per inch, is perfectly okay. If you're using something like acrylic and you just want a very light mark on the surface, then because it's a hard material, then you may well be able to get away with 300 or 350 dots per inch. So there are many factors that can affect the quality of your picture. But the key one is spot size and your choice of this thing called interval. Now, there is no single best way to prepare a photograph for laser cutting. If you go and check on YouTube, you will find there are lots of different demonstrations of how you can achieve this process. Sadly, none of them will go into the technical detail that I've tried to impart to you today. Now, that will be the success or failure of your end result, because like many things associated with this laser cutting technology, there is no absolute solution. This is a guide, and it shows you the things that you should be looking at. The one thing you can't do is just change the line spacing and the interval spacing, as I demonstrated to you before, because you'll get all sorts of aliasing effects and artifacts. So what you must do is make sure that you match the interval to the resolution of your picture. Now, you can experiment by changing that interval to a half or a quarter of your resolution and see what results you get. Go forth and experiment. Thanks for listening, and I'll catch up with you next time.